Today we're going to be taking a look at this new water cooling kit that has been designed for a Raspberry Pi 5. We're going to see how its custom water block and performance stack up against my DIY solution that I built for a Pi 4 a few years ago. I also used this solution on my Pi cluster, cooling 8 Raspberry Pi 4s at once. It worked really well for that, so I expect it'll work well on the more powerful Pi 5 as well. The water cooling kit has just been launched and currently costs $120. It includes a fan and water pump assembly along with a power adapter, some flexible tubing to run to the water block, and it also includes the installation hardware like some thermal pads and screws. The water block is a custom design for the Pi 5, and the kit comes with a heatsink for the bottom of the Pi as well. Next we need something to compare it to, and for that I'm going to try two different cooling options. The first is the active cooler that is designed for the Pi 5. This is a cheap and simple solution costing just $5. It's also commonly available. It's got an aluminium heatsink covering the CPU and surrounding heat generating components, and it's got a small PWM fan on it. The second's my original water cooling setup for my Pi 4. I've had to make some changes to it to work with the Pi 5, like redesign the heatsink bracket for the new CPU location. I've also strengthened the legs and holder for the Pi, as these were a little flimsy on the original. Other than that, it's pretty much the same set of components, especially the cooling loop. I'm going to use the same Raspberry Pi with each cooling solution for consistency. I'll just switch it between each solution for each test. I'm also going to be using the official Pi 5 power supply, so that we don't run into any power or under voltage issues. To test the thermal performance of each solution, I'm going to use a utility that I used to test my previous setup called CPU burn. This fully loads each of the CPU cores, and I'll leave this running for about 10 minutes on each, so that we reach the point of equilibrium every time. I expect the water cooling setups to perform quite well, so we'll also try overclocking the Pi to 2.8 GHz and see how each handles the additional overclocking heat. I did try get my Pi overclocked to 3 GHz, but I couldn't get it stable enough to survive a 10-minute stress test at this CPU frequency. I'm going to set up a thermal camera watching each during the test, so that we can see any hotspots. The thermal camera doesn't work on metallic surfaces, so it will be a bit limited, but we should still see any significant issues. Just out of interest, I ran the test first without any cooling solution connected, and ran into thermal throttling after about half a minute. It's evident by the drop in CPU frequency once we hit 85 degrees. For our coolers, let's start with the active cooler as a baseline. With the active cooler installed on the Pi, running CPU burn at the base frequency of 2.4 GHz, the starting temperature is 41 degrees. The temperature climbs pretty quickly, but starts to stabilize after about 5 minutes. And we have an average stabilized temperature of about 66 degrees. With the Pi overclocked to 2.8 GHz, the temperature starts at about 54 degrees and climbs a bit faster. This time it stabilizes after about 4 minutes at an average of about 74 degrees. At this temperature the fan steps up to its highest RPM, and this actually brings the Pi back down to 71 degrees quite quickly. It then floats between 71 and 74 degrees depending on the fan speed. I'm actually quite impressed by this result. I didn't expect a $5 cooler to handle a fully loaded overclocked Pi without thermal throttling. Next let's get the Pi fitted to the water cooling kit. Assembly is pretty straightforward. The water block obviously goes onto the top of the Pi, with a thermal pad between it and the CPU and some of the surrounding chips. The aluminium heatsink goes underneath the Pi. This provides a bit of additional cooling, but also protects the Pi and prevents any shorts on the contacts on the bottom if you've got it on a desk or workbench. I have to say that the custom water block with a copper base does look pretty good on the Pi, even if it's a bit unnecessary. It fits really well around the taller components and still looks like it'll allow you to hook up an SSD to the PCI Express port. We then connect up the flexible tubing between the water block pump and radiator. There isn't a place to mount the Pi on this assembly, so we'll just leave it on the desk alongside it. This is by design though, as the kit can be used with multiple Pis running in a cluster as well. Next let's fill up the loop with coolant and then boot up the Pi and start our tests. This block handles the base frequency of 2.4 GHz really well. We start off at about 30 degrees, then there's a small spike in temperature when the test ramps up, but the temperature doesn't climb much after that. It stabilizes after around 1.5 minutes at a temperature of about 45 degrees. With the power overclocked to 2.8 GHz, we now get a marginally higher starting temperature of 33 degrees. It again stays relatively flat, stabilizing after 1.5 minutes at about 51 degrees. So this cooling solution works really well, and we're still way under the thermal throttling limit for the Pi. Now let's see if my DIY version can compete with it. I used thermal paste for my Pi 4 build, but I want to try and keep the comparison fair. So I used a pad between the CPU and heatsink as well. I like that my solution has a place to mount the Pi, but the kit's custom cooling block looks a lot better than my simple square block and bracket. Through testing, similar to the previous solution, this block handles the base frequency really well. We start with a slightly lower temperature of 29 degrees, then there's a small spike in temperature when the test is started, but again the temperature doesn't climb much under full load. It stabilizes after about 1.5 minutes at a temperature of about 42 degrees. So actually around 2 to 3 degrees lower than the kit. With the power overclocked to 2.8 GHz, we again get a higher starting temperature of 35 degrees. It stabilizes after 1.5 minutes at about 49 degrees, so also about 2 degrees lower than the kit. So both the water cooling kit and my DIY solution work significantly better than the active cooler on an overclocked Pi. But the active cooler is actually quite capable of cooling an overclocked Pi at its full load as well. I'm a little surprised that my DIY solution with a simple aluminium block performed better than the kit's copper-based block. I assume that this is most likely because of a difference in the thermal pads. Mine has a really thin and good quality pad. Another possible reason might be that mine has more metallic surface area with the water, where the kit's block only has a copper surface on the bottom. The acrylic is a poor conductor of heat. I think the main benefits of a water cooling setup, besides looking cool, is that they have the capacity to cool a few more than one Pi. Typically a good 120mm radiator can dissipate over 200 watts. Given that the Pi 5 uses about 12 watts, even if all of its energy is being converted to heat, we'd still be able to cool over 16 Raspberry Pi 5s with one pump and radiator. So while these are overkill for a single Pi, they're actually quite a good cooling solution for clusters. There are some things I like about each water cooling solution over the other. The manufactured option has a really good looking water block, and it offers better coverage to the surrounding components. The cooling block from the manufactured kit is also available individually, so it's possible to buy one pump and radiator set and then use it across multiple Pis, which is also great. I do have some concerns that they've used copper for the cooling block and supplied an aluminium radiator, so you may run into issues with galvanic corrosion in your loop long term. I'd definitely stay away from using water in the loop, and I'd use proper coolant to try and assist in limiting this. My only other comment on it is that the included reservoir's return line pushes a lot of air back into the loop, which makes it quite noisy. My DIY solution is significantly quieter. I think my stand looks better overall and offers a place to mount the Pi, but I'm probably a bit biased. And as I've said, a water cooling solution is really better suited for a cluster, so the stand is unnecessary. I'll leave links to the kit and components in the video description if you'd like to get your own for your Pi 5. Let me know which solution you prefer, and also if there's something else you'd like to see me test on it. Thanks for watching. Please remember to like this video if you enjoyed it, and subscribe for more tech and electronics projects, tutorials and reviews.